This is video number 1 for sections 9.1 and 9.2, Simplifying Radicals. We come in chapter 9 to our fifth and final type of function this semester, and they are called radical functions. And just like in chapter 8 with the rational functions, we're mostly going to concentrate here on algebra skills. We'll do a little bit of graphing and modeling, but mostly algebra. Let me remind you of how radicals work. You can see one here. This symbol here is called a radical symbol. The number inside the radical symbol is called the radicand. And the tiny number up top here is called the index. And you remember that if the index is a 2, referring to a square root, then we don't write it. This expression is read the fourth root of 16. What does this mean? Well, you're looking for a number that you're going to multiply together a bunch of times. The index tells you how many times, and the radicand tells you what you want your final answer to be. So I'm looking for a number that I could multiply by itself 4 times, and the answer would be 16. Well, this one was made up purposely easy. That number would be 2. And you could go off on the side and verify for yourself that if you multiply 4 2's together, 2 times 2, 4, times 2, 8, times 2, 16. The fourth root of 16 is equal to 2. We have met radicals before in this class. I think the first time was in chapter 4. We had this rule about fractional exponents. We were trying to figure out the meaning of a fractional exponent, and we had this whole deal that said the top is the power and the bottom is the root. In other words, this simply means the nth root of our base raised to the m power. The bottom is the root, the top is the power. And we went back and forth between these two things. That means, for example, in our problem that we had, if I wanted to write that with a fractional exponent, well, let's see, my base is clearly 16. I don't see a power, which of course just implies that it's an understood 1. And I do see a fourth root. And so the top is the power, the bottom is the root. The fourth root of 16, another way to write that is 16 to the 1/4, which of course is also 2. In this chapter, we're going to focus not so much on the fractional exponents, but on the radicals themselves. And we're going to figure out what are different things you can and cannot do with radicals. In this video, we'll deal with simplifying radicals. Now, this is also something that we've done before. We tackled this just a little bit in chapter 7 when we were dealing with the square root method and the quadratic formula and all that stuff. Let me remind you what we did even back in that chapter. We've already done ones like this first example here. It says simplify the square root of 18. And let me, before I even address this list over here, let me just remind you what we did back in chapter 7. We said that if we could find a perfect square factor that goes into 18, we're expected to take it out. Perfect squares, you remember, numbers like 4, 9, 16, 25, 36, ... 2 times 2, 3 times 3, 4 times 4, etc. You can get as many as you need, of course, off the calculator. Well, if one of these guys goes into 18, I need to find it. Let's see, that would be, of course, 9. I want the biggest one that I can. And then once I find it, what I do is I split the radical up. I like to use the phrase good radical and bad radical. Remember, we're talking factors here, so I'm making a multiplication problem. I'm going to take that 9 that we got off the list, and let's see, 9 times blank, 9 times 2 would be equal to 18. So I've split square root of 18 into the product of two radicals, a good radical and a bad radical. Why do I call the first one a good radical? Well, because if it's on the list, it has a nice answer. The square root of 9, that just means what number do I times by itself to get 9? That would, of course, be 3. 2, it's not on the list, it's no good, I can't simplify that any. And so the final simplified version here would be 3 times the square root of 2. This box over here summarizes what we just did. Now I wrote it in a very generic way because see in a minute when we leave square roots, these 3 examples are all square roots, but when we go to other kind of roots like cube roots or fourth roots, instead of looking for perfect squares, we'll have to look for perfect cubes or perfect fourths, etc. But the process remains the same as we did in this first example. Okay, let's take a look at example number 2. This is still a square root. It's the same type of problem that we just did. This time, though, we've got a twist. We've got more than just a number in there. We've got some x's. Well, we should pause for a moment and think about what would perfect square variables look like. Remember, a perfect square just means something times itself, right? 2 times 2, 3 times 3. Well, the first perfect square variable would be x squared because x squared is x times x. Then if I did x squared times x squared, that would be x to the fourth. If I did x cubed times x cubed, that would be x to the sixth. Hopefully you're starting to see the pattern here. It's just going to go 2, 4, 6, 8, 10, etc. In other words, if I count by twos on the exponents, I can come up with perfect square variables. Again, make sure you're understanding why these things are on the list. X to the 10th, for example, is on the list because it is simply x to the 5th times x to the 5th. Remember, when you multiply 2 items with the same base, you add the exponents. You could do that same idea for any of the ones on the list. Okay, so we go to our example. We're going to split this up into the good radical and the bad radical. The good radical just means anybody on this list that is a factor of 50 or x to the 6th, and the bad radical will contain what's left. So let's see, start with the number 50. 50 is not on the perfect square list, but there is a factor of 50, namely 25, on the list. That means 25 goes in the good one. 25 times blank, the blank would be 2 to get me back to 50. Whatever I put in here, it better multiply together to get back to what I had. How about the x's? Let's see, x to the 6th. Ah, it's on the list. That means it's all good, and I don't even have any x's to put in the bad one. All that's left now is to go ahead and find these nice square roots. If they're on the list, they have nice answers. The square root of 25 is 5. The square root of x to the 6th, that just means what times itself makes x to the 6th. That would be x cubed. And the bad radical stays behind, and I'm done. This would be the final simplified answer for that radical. Okay, let's try the one below that. Same idea. I've got a few more letters here. That's okay. It's still the same process. The good radical, the bad radical. Let's see. The numbers, 4 is on the list, so it's all good. That means I don't have any numbers in the bad one. X to the 9th, not on the list. I want to take as much as I can, though. I always take the most I possibly can, so I guess that would be 8 of them that I could take in the good one, leaving me with that one extra 9th one in the bad. And then let's see, Y. That's just a single letter. That's not enough. I need at least 2 to be good, so the Y is going to have to go in the bad. Remember, everybody in the bad, it's stuck there. It's never going to change. That part of the problem is essentially done. All I need to do is work out the good radical, and that's very easy. Square root of 4 is 2. Square root of x to the 8th would be x to the 4th, because x to the 4th times itself makes x to the 8th. And then the bad radical, and I'm done. And here would be the final answer to that problem. Okay, so now let's try a different sort of problem here. It's the same directions. These are still simplify problems. But now I'm being asked to simplify a cube root instead of a square root. It is the same process as what we've been doing. It's just that now I need to be finding perfect cubes before I break up the radical and do the good and the bad and all that stuff. Well, again, let's pause for a moment and jot down our perfect cubes. For numbers, we'd be talking about numbers like 8, 27, 64, 125. Where am I getting these? 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4, 5 times 5 times 5, etc. If you needed more, you could get them off your calculator. How about for variables? Well, let's see. It would be x times x times x, which is x cubed. And then it would be x squared, x squared, x squared, which would be x to the sixth. And then x cubed, x cubed, x cubed, which would make x to the ninth. And again, hopefully by now you realize it's a very simple pattern here. 3, 6, 9, 12, 15, however far you want to go. The exponents are just counting by threes. These patterns with the x's are so easy to learn. Perfect squares, they count by twos. Perfect cubes, they count by threes. I'm sure you can guess already what's going to happen with the perfect fourths. Okay, now that my list is set up, I ought to be able to work the problem pretty quickly. So I go to my cube root, and I'm just trying to break it up into the good radical and the bad radical. Don't forget these little threes. If you forget them, it's incorrect. You'd be saying square root. Cube roots always break up into two cube roots. Okay, 24, not on the list, but 8 goes into 24, and it's on the list. So 8 is good, and that would mean 3. 8 times 3 is 24. 3 is in the bad one. For x to the 10th, I don't have 10 x's, but I do have 9 x's that I can take, leaving me with that 10th x in the bad one. And y's, let's see, I can take all 12. All 12 are on the good list, so y to the 12th. Okay, now I just need to take the root of the good factors, and I'm all set. Let's see, remember, they're on the list because they have nice answers. They have nice cube roots. The cube root of 8 would be 2, because 2 times 2 times 2 is 8. How about x to the 9th? I'm looking for something that I could multiply 3 of to get x to the 9th. Well, that would be x cubed. And then y to the 12th, the answer would be y to the 4th. Here's an easy trick you can use to figure out these powers here. All you have to do is take this power and divide it by the index. 9 divided by 3 is 3. 12 divided by 3 is 4. It works every time. The bad radical stays as is. Can't do anything about that. And so here is my final simplified version of that radical. We have one last example. It is a fourth root problem. All of the steps are going to be similar. We should just jot down quickly for ourselves the perfect fourths. The first one would be 16, followed by 81, and then 256, and so on. This just means 2 times 2 times 2 times 2, 3 times 3 times 3 times 3, and so on. You can get other ones off your calculator. The pattern for the variables we've already figured out. These guys are going to count by fours now. This is the sort of thing that on a quiz or a test you could always start by jotting down whichever of these lists kind of on the side of your paper, whichever one you thought you needed real quick, just so that you'd have it there to look at during the quiz or test. Okay, now that we've got the list, let's break down our radical here into the good radical and the bad radical. Remember, these guys are fourth roots now. 32 is not on the list, but 16 goes into 32 twice. So that's how that breaks down. X to the fourth, right on the list. It's all good. This other guy looks kind of funny, but don't overthink it. It's just a strange looking base, but it doesn't matter. It's just variable to the fifth. Is variable to the fifth on my list? No, but variable to the fourth is. So I can take 4 of those. I'll just have to put the fifth one over here in the bad radical. Well, everybody in the good guy comes out. The fourth root of 16 is 2. The other ones, just use that division trick. 4 divided by 4 is 1, so that's just an x. Another 4 divided by 4 is 1, so that's just a y plus 1. And then the bad stuff stays bad. Nothing I could do with this stuff. And I'm done. I know these are not the nicest looking answers, but if you can take stuff out of a radical, that is always considered better than leaving it on the inside.